chi-squared test homogeneity of proportions, which is when we have two populations and we ask one question. And we're going to do an example using methods for treating epilepsy, and those methods are surgery or drugs. In a study reported in the SGV Tribune, 15 of 36 patients who had a chunk of their brain removed were free from seizures a year after the operation. However, only 1 of 40 patients who received the standard drug treatment were free from seizures. Is there a significant difference in the effectiveness of the treatment methods? So we're going to go ahead and use the calculator and do a homogeneity of proportions test. We could do it by hand, but nobody wants to do that. And here's our observed data. We put it in a nice two-way table. So go to your calculator, and if you go to second x to the negative 1, nope, I hit the wrong button. You see matrices, and we're going to want to go to edit, enter, and we have a 2 by 2 matrix. We had 15 people who had the surgery that were free from seizures, 21 who were not, 1 person who just took the drugs that was free from seizures, and 39 who were not. Once you have that in, go to second quit. You can go back into matrices and hit enter to verify your data is correct. And now we're going to run our tests. When we go to stat, test, go down to chi-squared, not the GOF. GOF is just for one row of data. So this one. And we tell it our observed data was an A. It'll put our expected data in B. We're going to ask it to calculate our statistics for us. And there we go. Our chi-squared value is 17.48 or 0.49 with a p-value of almost 0, 2.89 times 10 to the negative 5, and 1 degree of freedom. We can then go into second matrix, so after we write all that down, and look in our B matrix and see all of our expected values, which we have to check and make sure all are greater than 5, and they are. Let me flip back to the notes. So I have written down my chi-squared values, and right here I have my expected values. You don't have to go out 4 decimal places. 1 or 2 would be just fine. If you're doing it by hand, you'd want to go out as many as possible. And now when looking at it, notice that what we observed was not what we expected. Okay, the values are different. So that leads us to our 5-step test. At first glance, it appears that the treatments are not the same since the observed counts are different than the expected counts. However, it is possible that the treatments have the same effectiveness, and we got these differences due to randomization variability. Again, it's randomization variability because it was treatments applied to people, not just a sample, although they're assuming that it was a study and it was an experiment of doctors doing this experiment. If they had just asked people who had these treatments instead of randomly assigned who got what, then it would be sampling. And anyway, to decide, I will conduct a chi-squared HOP test with an alpha of 0.05. So my null hypothesis is that removing a chunk of brain and conventional drugs have the same effectiveness, and the alternate hypothesis is that they don't. So I really like this example because it makes it kind of clear the difference between the homogeneity of proportions test and the independence test. Remember, the independence test was what we talked about in class, where it was, does gender affect movie choice? This one really makes it clear in that, did the drugs have the same effectiveness? Okay, and now we're going to look at the conditions where the treatment's randomly assigned. We don't know. We're going to assume so maybe we would proceed with caution. Was the sample less than 10% of the population? This is obviously wrong. It should be yes. Okay, so yes, there are more than 400 patients in each population or in each group. You could also, and that 400 came from, of my 2 different populations, this one was the biggest, and 40 times 10, because this would need to be less than 10%, is 400. I guess you could also compare it to the 76. But for every example that I've looked at with AP, they go towards the largest population size in each group. And then, as long as we don't want to generalize results to the whole population, we can skip A and B, although it'd be nice to be able to generalize those results. And the most important thing is a large enough sample size. This one you always have to say. And notice the expected counts were all greater than 5, which we did. So now, going back to what I had from the calculator, we could have done it by saying the observed value, and our first observed value was 15. 15 minus 7.57 squared all over 7.57 plus dot 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 all of the different values, okay, is equal to a chi-square value of 17.5. Our degree of freedom was row total minus 1 times column total minus 1, or 1, and it was a p-value of almost 0. It might be better to write the actual scientific notation decimal there, but for time's sake, I'm just going to say it was almost 0. So let's go ahead and conclude then. Since our p-value was less than our alpha value, I can reject the null hypothesis and conclude that the true treatments do not have the same effectiveness. A really common question is, why can't we conclude that surgery is better? Because it looked like it was based off the data. I mean, 15 people free versus 15 out of 36 versus 1 out of 40 free from seizures. And that is because our test was two-sided. So it's just saying there is a difference. We can't conclude that one version is better than the other. Okay? We just have to do it's different. Could we have done this test another way and maybe been able to conclude that? Well, because it's a 2x2, or just 2 populations but 1 question, we absolutely could have. We could have done a 2-sample z-test for difference of proportions instead, and then we could have done it as a 2-sided test, which again we would just to conclude that it was different, or we could have done it as a 1-sided test, and that would have been great as well, and then we could have said, yes, we actually think surgery is better. And so if we were to do that, we'd have to list our P1 and P2. P1 would be the proportion of patients who have had surgery that have had no seizures, And from our sample, that gave us a p-hat of 1 being 15 out of 36. And then if we did the other one, the proportion of patients who use the drugs that have had no seizures after a year, that would be a p-hat for proportion 2 of 1 over 40. Okay, if you subtracted the 2, we would get a difference of 0.392, which is greater than 0. So it looks like they're not the same. So if we wanted to do it as a 2-sided test, we do the probability of the difference of the proportions being greater than 0.392, which is the probability of the proportions being greater than a z-score of 4.18, which is actually, I've got into the 2 proportions z-test screen so you can see it, the 15 out of 36 and the 1 out of 40, and if we did the greater than, because we think this one minus this one would be greater than 0. Okay, that's actually a proportion, or a p-value, if you look right here, of 1.44 times 10 to the negative 5. And that would be a pretty small p-value, so we could reject the null hypothesis. And if our null hypothesis was the difference was greater than 0, we could conclude that the brain removal was better than the conventional drugs. However, when we want to truly just mirror what we did with the chi-squared, we would need to do a 2-sided. So we change it to the not equal to. So again, we couldn't necessarily say there was anything more than a difference. And that's the same as timesing the p-value we just got by 2. Okay, and now we have a p-value very close to 0.00003, because this would round up to 3, and we have 10 to the negative 5. Let's go back to the notes. Okay, I've gone ahead and written down when we did it as the P1 minus P2 being just greater than, we got this p-value, or you can see it was this. And then if we wanted it to be a not equal to, okay, which would be the two-sided, we'd times this by 2 and get the one we got the second times I did it. So there's the times by 2 and the times by 2. Anyway, we get a p-value of 0.003. Note that the p-value here was the same as the p-value for my chi-square. And I'm going to go back and write what it was out of the calculator so you can see that. I forgot about that. I'm going to run this chi-squared test again, and you can see it's 2.89 times 10 to the negative 5, which would be the same as 0.00003, the same as the one that we got using the other test. So again, notice this was the p-value for the chi-square test that we did. Go to the difference of proportions. P-value is the same. And then notice my z for this one was 4.18. That is the same as my chi-squared value if we square the z-score. So 4.18 squared is approximately 17.5, which is the same thing as my chi-square value that we had right here. So they do relate. And honestly, if I was going to do this as a statistician, this is not one that I would do with a chi-square. Also, to truly be more accurate, you need to do a correction. I would do this one with a difference of proportions. And so let's just clarify. When the degrees of freedom is 1 and the test is two-sided, the homogeneity proportions test is the same as the two-sided two-sample z-test. However, if the table is greater than a 2 by 2, you must use chi-squared. And if the table is 2 by 2 and the alternate hypothesis is one-sided, you must use the z-test. Also, when doing a goodness of fit test, there are only two categories. Degrees of freedom equals 1. This is equivalent to a sample size of a 1 sample z-test for proportions.